Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about the electric circuits. So last time we have already discussed a little bit about the currents as well as the voltage. And so now we want to use all of these knowledge to create circuits for you to store information as well as to do certain things. So before getting started, please consider subscribing as well as liking the video, and also please check the description below for the notes in this entire discussion. So let's start with the electric circuits. And before we get started, we need to first know about these circuit symbols. So pretty much, what is a circuit? So a circuit is pretty much multiple different components of circuit elements, which when combined together will do certain things. So that's the easiest way to actually to describe such thing. So what are the symbols involved when you're dealing with circuits? So you have the resistor, you also have the capacitor. Those are the two things that we have already discussed previously. And also sometimes I do also write the voltage source, or sometimes you could call it as the EMF or the electromotive force. So this is one word that I will normally use, the EMF, the electromotive force. That's pretty much the entire symbol that we will probably be using, except for another one, which we'll call that as the ground. So the ground is pretty much where you take the reference point, where normally this is 0 volts. So apart from these components, you do also have some measurement devices such as the voltmeter as well as the ampere meter, which I will later try to discuss a little bit about. And then you do also have a way for you to input things, which is by using a switch. And also sometimes the resistor as well as the capacitor could be changed depending on your desire. So something like a resistor, and then you could actually change its value. We will call this as a variable resistor, something like this. And same thing for capacitors. You could have the sign. So what exactly is the electromotive force? So pretty much the EMF here pretty much represents the source of voltage. That's the easy way to describe such thing. But in here we will actually only be assuming an ideal EMF, where there won't be any energy going out of this source. And we will later discuss about the real EMFs, which are pretty much batteries. So let's get started on actually discussing a little bit about the connections between a circuit. So remember when we deal with capacitors as well as springs, we discuss about series as well as parallel. So now I want to describe what series is again. So series is pretty much where you put your components together in a single branch, while parallel, you put them between multiple different branches. And each of them has certain properties involved around it. So I want to try to discuss a little bit about the series connection of resistors first. So this is R1 and also R2, and I will just connect this to a EMF source. So there's a positive and there's a negative. So pretty much the long side is the positive. So based on your knowledge from the previous chapter, you would know that the current should go in this direction. So it will go from a high voltage towards a low voltage. And remember when we deal with conductors, pretty much a conductor should have the same voltage all around. So this entire object will have voltage, and this object also has the same voltage. And in here, it should have the same voltage as well. So in here, this will be with the value of V. So sometimes, like, you could also draw EMFs with using two of these long and short bars. So that's what we call as the V. So remember about voltage. Voltage is pretty much a state variable, first of all, and second of all, it is pretty much dependent on your reference point. So that's something for you to also remember. So you couldn't truly state the voltage at a certain point. Instead, you could say the potential difference. So let's actually just try to write this down. So there will be a potential difference from here to here and from here to here. So this is what we'll call as V1 as well as V2. So something to deal with when you're actually dealing with circuits is that if you have a loop, something like this, so when you try to sum all of the voltages, if you sum off the voltage, it would be 0. So there will be some components, and components. It all has to be 0. So this is the same logic when you're dealing with circuits. So let's just actually take the path from this way towards this direction. So pretty much the sum of voltage literally depends on your direction, on where you're counting it. So if we actually do this clockwise direction and compute it, we will first cross the source of the voltage. So it will be negative V. And why is it? No, actually let's just actually make it V. So you do see that there's an increase in the voltage. And then after that, it will later pass through this first voltage. And passing through this first voltage actually reduces its voltage, which will be the negative V1. And this pretty much also works within V2. It also decreases. So pretty much, how do you know when something is increasing or decreasing? So if it goes from the negative to positive, that means that the value is increasing. That means that it's positive. While the other way around means that it's decreasing. But remember, this is all just notation. So you could just write the notation to be something else, in which that you could have it to be negative V plus V1 plus V2. But in here, I will try to describe it by the increase or decrease in the potential difference. So this should be 0. So another knowledge that you get from the previous chapter was, so I will need to describe this for you first. So if you have a wire and you supply a current, in order to make sure that this object will have a net current of 0, a net charge of 0, means that it has to also exit out the same amount of current. So this is pretty much the same thing when you're dealing with fluids. It's like the mass going in must equal to the mass going out. So this is also another property in which the sum of the currents must equal to 0. Or pretty much the sum of the current at a point must also equal to 0. So with this, we could actually see that there's current going in here and then current going out. It should be the same. And that means this value will later meet with this R1. And remember about resistors, the voltage is pretty much I times R. So we do know that this is pretty much the voltage equals to V1 plus V2, which is I R1 plus I R2. So notice something in here. We could just write this down to V equals to I R1 plus R2. Well, that's interesting. And this is because this pretty much looks like the Ohm's law. But instead of using the R1 or R2, we use the sum of it, which is the R equivalent. We call it as the R equivalent. So this is the so you could just draw something like this, in which you have only one resistor. You call this as the R EQ, and then there's current going here. This works the same way. So we know that that you could actually just evaluate the circuit just by only summing up the resistors, as if you could just combine them together into one. And this actually works for multiple different resistors within series. So you could state that this is about, so if you have, so the R equivalent for series will be the sum of the RIs. So it's starting from I equals 1 to n. So you just need to sum all of them up, and that's for series. So I will later try to discuss a little bit about real batteries, but for now I want to describe a little bit about the parallel circuit. So instead of putting everything into one branch, we'll just split it up between two different branches. So same idea, R1, R2. There's a positive and a negative. And there's current going in. So it goes from the positive towards the negative terminal of this voltage source. So let's actually check about this again. So there's V1 as well as V2. So first thing that you would actually need to realize is that the voltage of this entire object here is the same, and the voltage in this entire object must also be the same. Therefore, you could figure out that V1 must equal to V2, which should also be the voltage. So after that, we could actually just look at the current. So let's actually look at this green component here. There is current going in, and then there's current going out. And we'll just call the current to be I1 as well as I2. So we know that I should be I1 plus I2. That's pretty much what you get from this theorem, in which the net of the current must be 0 within the node itself. And this pretty much also works at this other point. So you would see the relation I equals to I1 plus I2. So by also using Ohm's law, we could get V over R1 and V over R2, right? So we can just write this down as I equals to V 1 over R1 plus 1 over R2. Now, you could now see that there's this other similarity, in which that this is pretty much the same thing as I V over R, or R equivalent. So here's something interesting. The reciprocal of the equivalent resistance is pretty much the sum of the reciprocal of the resistance, which sometimes you could call it as conductance. So it's the same thing as you draw something like this. So you do see that there are two different ways for you to add up resistors. One of them in a series way, and then the other one is in the parallel way. So there are different names involving around these two circuits. The first one here is something which you call as a voltage divider. Why is that a voltage divider? So if you actually try to compute the voltage at each of the resistor, you would get, so V1 should be IR, right? IR1? Right. So this would be, so the current is the V over R1 plus R2. So it's VR1 over R1 plus R2. And for V2, it will be VR2 over R1 plus R2. So you could see that instead of each resistor taking the whole voltage, you are pretty much splitting it into two. So this pretty much helps to actually to protect the resistor, because if you actually just only use one resistor and it is trying to expel all of this energy in the form of heat normally, it could end up catching in fire because of the high temperature it is producing. So by using this voltage divider, you could actually split up the heat emitted into multiple different resistors, which could actually save your circuit. But in here, this actually is sometimes called as the current divider, in which you are actually pretty much splitting out your current. And you could also compute for the current, but I won't be doing it here. So, like I mentioned last time, I want to discuss about the battery itself. So, the best way for me to describe a battery is that you would have a EMF source, and then this is the load, the R load. And then in here, I will also introduce another resistor, which is the internal resistance. So pretty much batteries couldn't truly work as like an entire voltage source, because if it is totally a voltage, because inside of it is like pretty much there are wires within it, so it couldn't be truly be a conductor. So therefore we need to introduce the concept of the internal resistance. So this works as a series or a voltage divider circuit. So in actuality, pretty much this R load here is like much more greater compared to the Rn. So pretty much all of your work or energy goes here. This is much more if the R load is greater. But what if I put, let's say for example, no resistor there, like calling it as a short circuit, where you put two wires literally from one end to another straight away? Well, the battery itself is gonna release the energy, which means that your battery could heat up and probably do some crazy reactions within the battery. Because remember, batteries inside of it contains electrochemical reactions. And by addition of heat, it might cause certain things to maybe even blow up. So, with this knowledge of series and parallel, you could actually design a certain resistance through applying multiple of these resistors. So let's say for example, if I have like this kind of circuit in which it just attaches to a EMF, we call that as V, and the question is, what's this entire thing as a R equivalent? There are multiple ways for you to do this. First of all is that you could actually just create the circuit and then measure it using a ohmmeter or a multimeter, and you could see that there is a certain amount of ohms, which is the R equivalent. Or another way for you to do it is by actually to do it mathematically. So this R equivalent here, that's pretty much R1 plus this R of the parallel, right? And this R of the parallel can be written as 1 over RP, or the sum of no, not not really, it's 1 over R1 plus 1 over R2. So you would get R1 plus R1 R2 over R1 plus R2. And this is the equivalent resistance. So pretty much you already have the tools you need just to create a resistor or even a circuit, and you just want to pinpoint what the resistance is without even computing what's the circuit, no, what's the current in between the nodes or the potential difference between each of the components. So you already have the tools you need just to compute the resistance of a circuit, right? But maybe, let's say I give you a certain kind of circuit, and I want to ask you just to try to compute what's the resistance between from this point to this point. So this black box will be a resistor there, a resistor there, a resistor there, a resistor there. So you might be thinking, well, this is pretty much just a parallel circuit. Inside of it, there's a series within it. But what if I introduce another resistor inside of it? How would you try to figure out what's the total equivalent resistance? So this might be a very hard thing for you to do. And it turns out that it is. It is hard for you to solve it without using Kirchhoff's law. So what exactly is Kirchhoff's law? So there are two types of Kirchhoff's law. The first one is something which you call as KCL, or the current. So take any node. So a node must have the sum of I to be 0. And there's also KVL. A loop must have the sum of voltage to be 0. So this is pretty much the idea that we have already used. We literally assumed that voltage is a state variable, and we also assume that there is no charge buildup. And that's actually Kirchhoff's law. But here's something that I need to mention right now. Not everything can be computed using Kirchhoff's law, because Kirchhoff's law only knows these certain condition. The first one is the speed. If you have the current to be traveling faster than light, or no, sorry, very near the speed of light, Kirchhoff's law won't hold because of you didn't consider relativity into it. And second, you would also need to consider about the magnetic field. Energy can be lost through the magnetic field, which is pretty much related to the electric field. And by knowing that there's a magnetic field applied to the system, let's say, you would know that there would be additional energy going in, or there could be additional energy going out through the Ampere's law. But I won't fully discuss much about the magnetic field. And lastly is also the size. We assume that the entire object was a lumped object, a lumped element. And if you go into a very small scale, quantum mechanics will also have certain things to apply when you're dealing with this very nanoscale wire, let's say, or like, yeah, microns. So this only works when you're dealing with pretty much sizes of resistors or capacitors, pretty much on that scale. And also there shouldn't be any magnetic fields. But throughout this discussion, I want you to remember that we will be neglecting all of these, and we'll just say that Kirchhoff's law will hold. So, I want to try to describe what exactly KCL and KVL truly means, but I won't be fully solving the entire Kirchhoff's law for this Wheatstone. So I'll just use a red pen and actually travel it throughout this entire circuit. So notice here, there are, so let's just put this in, no, let's just do it in red first. So let's count about the number of loops that we have. So we can go from here, and we can go in this direction, going in this direction, and then going back. You could also go from the same path, but you go from this direction. And then you go back down, and then go back into the entire circuit. Or you could also maybe even cross this middle section. And there are much more different paths for you to take, but by only using a certain amount of these loops and then figuring out its KVL, you would get a system of equation in which you could actually solve the voltages between each of these elements. And that's the thing that you would need to figure out, because after knowing the voltages, you could actually figure out the current. And you could also do the same thing, but instead of using the voltages, you could just use the currents. So you could just analyze the current inside there, inside there, inside there, and maybe even inside there, but it's not really relevant, so I'll just deploy an X in there because it's not really necessary. So with this equations, you could actually solve what is the currents, what's the voltage, and what's the and pretty much the R equivalent of this entire system after you know all of these things. So it's very useful when you have already started to deal with multiple different branches of networks going on. But I won't fully discuss a lot about the circuits, but if you want some discussion in circuits, please tell me in the comments below so that I can actually discuss a little bit more about circuits. But anyways, let's go back to the discussion again. So people might be thinking, how do you actually use a ampermeter or a voltmeter or a ohmmeter? Well, in here I'm going to try to actually to describe how do you actually technically use these things. So first, let's actually talk about the voltmeter. So the voltmeter itself pretty much measures the potential difference between two different points. And the way that you would actually do this is by actually taking, let's say you have a voltage and then probably some resistance as well. And we'll have this object, I don't know what it is. And I want to measure the voltage in between these two things. So something to remember is that you don't put the voltmeter in here, because you are pretty much just comparing one node as well as the other node. You're pretty much comparing the voltage. So you would need to compare it in here. This is where you put your voltmeter, and it will later display what your voltage is. But this does not work for ampermeter. So for a ampermeter, we would have another black box. And let's say I want to know the current passing through this object. Well, instead of you putting it here, which is pretty much your giving another path for the circuit, instead you put it inside of it. And this will measure the amount of current passing through the instrument itself. So a voltmeter is used by attaching it parallel, while a ampermeter is by attaching it in series. And why is that? So technically, a voltmeter actually, so pretty much a voltmeter is pretty much a resistor, but it's a very big resistor. It's so big to the point that it is actually pretty much like a open circuit. But you could actually still sense some current passing through. And if you are able to measure such currents, you could create a voltmeter just by multiplying it again by your resistance. And for ampermeter, it's pretty much a another it is pretty much another resistor, but it's very small, to the point that it is pretty much like a straight wire, and you can technically figure out what's the voltage in between these two things. And if you know the voltage, you could divide it by the resistance to get the current. And so I think like the easiest way to actually to figure out is to measure the current, because you could use the current just to measure the magnetic field, which could actually become a basis for your measurement. Or if you have voltage, you could have a charged particle, let's say, and see where it would move. So there are multiple ways for you to create a measurement device for a voltmeter as well as the ampermeter, but the one that is commonly used throughout our lives is the multimeter, which pretty much combines the voltmeter as well as the ampermeter, and also the ohmmeter. So how does the ohmmeter work exactly? So it's pretty much applying a certain voltage, and you're trying to measure its current. That's how it works. And then if you know the voltage as well as the current, you could figure out the resistance. So that's exactly how measurement devices work when you're measuring current or even voltage. So we should now start to talk about the capacitor, which we have already introduced last time. And let's just actually do something interesting. What if I just put, let's say, a resistor as well as a capacitor here? So remember one thing. A capacitor stores energy in the form of voltage or pretty much electric field. And let's just assume that is zero. So let's say that the voltage here is zero at the initial time. And then we have a resistor, a capacitance, as well as the voltage, which I will call that as this E. So let's just actually try to compute what is the voltage in between the capacitors. Even though we know it's zero, but we should try to do this mathematically first. So we will just pass through this clockwise again, like normal. We would find that a negative of this E, no, sorry, sticking to the convention, it's E minus the voltage from the resistance minus the voltage from the capacitance, which should equal to 0. Now, so we can write this VR as I times R, and the VC is something interesting. We know that Q over VC should be C. So we could write this as Q over C. Now, it might seem that it doesn't really work, right? But actually, if you actually just take the derivative of this, the d over dt, well, this E here, I'm going to assume this to be a constant anyways. This is going to be 0, which equals to the di over dt. Multiply that by R, subtract that by negative dq over dt. And that's actually the current over C. So what we get is actually a differential equation in which you could actually solve this to get I equals to, oh wait, did I did this correctly? Whoops, it should be plus. So I should be E something times e to the power of t over RC. So this RC here is something which you normally call as the time constant. So this is pretty much the time constant when you're dealing with these kinds of like differential equations. And so with this information, remember what we were asking at the very start. we want to know about the voltage. So let's actually try to figure out what's the voltage. So what we got here is I, right? And we know that from here we could just derive this again. I is pretty much d over dt. It's c dvc over dt, right? So we need to do the integral of this to get our voltage. So if you integrate this over dt, it should get c vc. So let's actually divide this by c. So integrating this, we would get a, the integral of that, it should be e to the power t over rc times rc. Divide that by c. So you would get ar e to the power negative t over rc. And that's the voltage at here. So now, with this information, and also our initial condition in which we assume that the energy was 0 at the first place. So this should equal to 0 when t equals to 0, right? Therefore, oh wait, there's something that I did wrong. Ah yeah, this should be from 0 to t, my bad. So it's, yeah, that guy minus 1. So technically it's that. So if you apply t equals to 0, the Vc would be 0, right? So that means putting it in, it should all be 0. Yeah, it makes sense. So we know that the voltage in between these guys are 0. And that means we could actually compute what's the VR now. And why do I now just by sudden shift into VR? And it is actually because of one thing. If we actually try to figure out the VR, because we know this is 0, and this is, and the, oh wait, no, actually coming from here, coming from this guy, we know Vc is 0, that means VR should be epsilon, right? No, sorry, that's the EMF. But we also know that VR is actually I times R. So we could write this as I times R. So we know that the current at time equals to 0 is epsilon over R, which actually brings up something. This current and this current should be the same. So applying 0 to it should also imply that this and this should be the same. Well, that's exactly it. So actually the solution is I equals to I0 R, no, I0 e to the power t over RC. And the voltage is I0 R, which is actually the EMF multiplied by t to the power negative t over RC minus 1. So why did I actually compute about this? Well, we do see that the voltage actually changes after you apply a certain current. Oh wait, actually there should be a negative sign somewhere. Ah yeah, there's a negative here. So this should be actually technically negative. Yeah. So it's technically negative there. So it's actually negative epsilon. Yep. So this is epsilon 1 minus e to the power of negative t over RC. So with this, you could actually try to plot this in a graph, comparing Vc as well as the time. So starting from time equals to 0, it's pretty much 0. And then when time goes to infinity, we know that this value will approach 0. That means that it will approach this EMF. So it will have a graph something like this. So it is pretty much a exponential curve in which it has its maximum voltage at the EMF. And this is where the current actually goes to 0. So when time goes to infinity, the I would also go to 0. So it means that there won't be any current passing through the capacitor. So something interesting is that if you actually take out the capacitor itself, remember that it doesn't actually, because like if you have, let's say, this guy here as well as a very big resistance here, you would know that, well, yeah, technically it's actually short. So if you have a capacitor and then the thing is shorted, the current won't have anywhere to go. So the charge will be kept in place until you apply a certain resistor into it. And this is the next thing that I want to discuss, which is the discharging of the capacitor. So maybe we should actually try to think about this now. What if I already have this guy to have its VC to be the EMF, let's say, at time equals to 0. So we now change the question. And we will actually try to figure out what will be the shape of the potential after time equals to something. So let's do the same trick. So instead of that, we'll actually just draw it like this. So it has V equals to epsilon, and then it has a resistance. So let's try to crack this open. First of all, we will actually introduce the direction, and let's say this is the positive side, this is the negative side. So this is much more higher compared to that one, and vice versa. So we see a negative VC plus the VR. No, technically no, it's the other way around. Equals to 0. So this means that our VC equals to VR, right? And VR is IR, as the current is going to go in that direction. And VC, we know that to be Q over C. So this is Q, this is negative Q. So now, what I want you to realize is that in here, we will actually have this current going out of this Q, which means that if you actually take the derivative, it's technically the negative no, it's actually still dq over, it's still dq over dt, but the dq over dt in here is pretty much the negative of the current. That's something to realize as well. So you need to make sure that you still remember your signs, because it could mean that it is at the positive side or it's at the negative side. So you would get this. And solving this, we would get the I to be e to the power of negative t over rc with another constant a. And maybe like, and actually you could actually just use this information straight away. When time equals to 0, we know that the current should be epsilon over r, because we know that the VR should also be R, because this is actually VR. So with this information, we could actually just rewrite this straight away into epsilon over R e to the power of negative t over RC. So if we actually try to do the integral of this to get our V, we would get the epsilon e to the power of negative t over rc. Yeah, just that. So if you actually try to integrate it, you would get this. So this graph will be represented as something like that. So this is voltage and this is time. So you do see that the graph is like very similar to the charging. So you could actually charge a capacitor as well as you could discharge a capacitor. So now you see that pretty much that current doesn't always mean it is proportional to voltage. And same thing with voltage. Voltage is not always proportional to the current, as you can see with the capacitors. And this could actually create multiple different kinds of devices. One of them is storage information, in which you just put charges into a capacitor, so you could have a high voltage or maybe even low voltage, and then later you could actually use like a voltmeter just to measure if it is above 5 volts or below 5 volts, and that will be your ones and zeros. And then later you could create another circuit that pretty much does addition, let's say. So pretty much you could actually do logic. No, sorry, not really logic, but storage within capacitors and also resistors as well. And you also figured out how do you actually clear those informations. Now, now it might be a little bit hard if you actually always use the relation that I no sorry that V is Q over C. This might sometimes be too much to the point that you might need to find a better way to to rewrite this equation as a electrical engineer. And it turns out that there is a way. So let's actually derive that. So V equals to Q over C. So it will be pretty much the voltage difference here. This is the Q, this is negative Q. And let's state that going here is I. So taking the derivative, the dV over dt should equal to di over C. Because if the I is positive, it means that there's buildup of charges. So we would get this relation. So you could write this as the I equals to the C dV over dt. And this is the relation that is normally used when you're dealing with a capacitor when you are a electrical engineer. So now this information is very useful when you're doing KCL or even KVL, because now you have a direct relation between current as well as the voltage. So that's all for today's discussion. So I hope you fully understand about circuits, even though I don't fully discuss a lot about examples. But if you want more of these videos, please consider subscribing as well as liking, and also please share this to the people who really needs this information so they can understand physics in a much more better understanding. So if you want me to discuss more about electrical circuits, please write them in the comments, and maybe even the circuit itself, so I can guide you through understand circuits much more better. So thank you very much, and I will see you on the next video.